Welcome to matrix multiplication and dot product, the math behind AI's magic. Today, we're going to demystify the fundamental operations that power nearly every AI system you interact with daily. By the end of this lesson, you won't just know what these operations are, but why they are indispensable for building intelligent applications. Our journey will cover three key objectives. First, you'll learn to master matrix multiplication, understanding its role as the core of every neural network's forward pass. Second, we'll dive into implementing dot products from scratch, gaining a clear insight into how AI systems quantify similarity between different data points. And finally, we'll bring it all together by building a simple recommendation engine, much like the ones used by major streaming and e-commerce platforms, demonstrating these matrix operations in a practical, real-world context. Let's begin. When you interact with AI every day, whether it's asking a chatbot a question, getting a personalized video recommendation, or seeing product suggestions online, you're witnessing matrix multiplication in action. It's the hidden engine behind these experiences. Every single prediction, every calculation of similarity, and every layer within a neural network relies on these operations executing thousands of times per second. Think of matrix multiplication as the multiplication tables of AI. Just as you needed to master basic arithmetic before tackling algebra, understanding how matrices multiply is essential before you can truly build or even fully comprehend intelligent systems. Today's lesson is designed to transform these abstract mathematical concepts into the practical, foundational knowledge that makes advanced AI systems work. It's not just theory, it's the bedrock of practical AI. At its heart, matrix multiplication is far more than just mathematical gymnastics. It's how AI systems transform and combine information. Imagine you have a matrix representing various movie features, like their scores for action, comedy, or romance. And you also have another matrix detailing different users' preferences for those same genres. When you multiply these two matrices together, the result isn't just a jumble of numbers. It's a brand new matrix that tells you precisely how well each movie matches each user's individual taste, effectively generating recommendation scores. In Python, if you multiply a 1000 by 5 matrix of movie features by a 5 by 3 matrix of user preferences, you get a 1000 by 3 matrix. Each cell in this resulting matrix directly shows how much of the 1000 movies appeals to each of the 3 users. It's a powerful way to distill complex data into actionable insights. Beyond basic multiplication, the dot product is AI's incredibly powerful similarity detector. It measures how similar two vectors are, and its applications are truly endless. For instance, in natural language processing, it can tell you how semantically similar king and queen are by comparing their word embeddings. In image recognition, it helps determine how much a specific image patch matches a learned feature. And in recommendation systems, it can quantify how similar two users' preferences are by dot producting their rating vectors. The formula is simple: multiply corresponding elements and sum them up, but the implications are vast. Furthermore, in AI, matrix dimensions tell a critical story about your system's architecture. The shape of your input layer, weight matrices, and output layer directly dictates how information flows between layers. Getting these shapes wrong in matrix multiplication is like trying to plug a USB cable in upside down. It simply won't work. But get them right, and you've accurately described the exact architecture of your neural network. Finally, let's talk about broadcasting, AI's smart shortcut. Broadcasting allows you to perform operations between matrices of different sizes, following a set of intelligent rules. This feature is incredibly crucial in AI for several reasons. It enables you to efficiently add bias terms to all neurons simultaneously, apply the same transformation across all training examples without explicit loops, and normalize data efficiently across entire datasets. It's a powerful abstraction that simplifies code and improves performance. To recap, we've explored how matrix multiplication is the foundational operation for neural networks, how dot products detect similarity across various data types, and how the precise shapes of matrices define AI architectures. We also touched on broadcasting, a clever mechanism for efficient operations.
By understanding these core concepts, you now have a stronger grasp of the mathematical engine driving modern AI. For a quick self-assessment, consider this. How do matrix shapes impact the design and functionality of a neural network?